Okay, let's pick up where we left off before. So we said what's going to happen if the compounding becomes continuous, so all the time. And how will this formula change when n gets bigger and bigger? So we'll start off with sort of a clever substitution. We're going to let m be n over r. Basically, we're letting m be the reciprocal of this guy because it's going to make our proof or justification follow nicely. If m is n over r, then its reciprocal 1 over m would have to be r over n, right? So we'll come over here in our formula and replace r over n with the 1 over m. And we're also going to go ahead and say, hey, if I cross multiply this, I'm going to have n equals mr. So my exponent nt, the n part, will get replaced by mr. So now I have p 1 plus 1 over m, and I'm going to apply, let me put it all together, mrt. And I'm going to apply properties of exponents and pull this exponent inside. That's going to be p 1 plus 1 over m raised to the m, everybody raised to the rt. Now as n goes to infinity, m goes to infinity also, because you have n getting bigger and bigger and m getting bigger and bigger, which means this guy, as m goes to infinity, this guy approaches e. That's what we showed at the beginning of the lesson in the previous video, that as that variable in the expression gets larger and larger, we're going to end up with e for that expression. So I have e to the rt as my exponent waiting outside, p is waiting outside as well, and I have a equals p e to the rt as my new formula for compounding continuously. So if n is like yearly, semi-annually, monthly, quarterly, daily, you essentially use the big formula and put those values for n. If it's being compounded continuously, then we're going to use a equals p e to the rt for our formula to compute how much money is sitting in your account. Now let's go look at some examples. Let's say you invest $1,000 at 5% interest yearly for 3 years. So you're getting interest 5% and the money is sitting in the account for 3 years. How much money is in the account after 3 years if it's compounded quarterly? So for quarterly, we're going to use n equals 4, and we're going to use the big formula. 1,000, that's p, that's r, that's t. 1 plus 1 over n is 4, to the nt, r over n. Let me fix that. 0.05, that's r over n to the nt. So 4 times 3. That's going to be 1,000 times 1.0125 raised to the 12, which is going to give us that 1160.75 that we had looked at before in the previous video. Part B is the same thing, but now you're compounding it monthly. And as we saw in the previous video, now that you're applying interest more frequently, meaning 12 times a year, you're going to have NT 12 times 3, and we ended up with 1,000 times 1.004167 to the 36, and we saw that you make a little bit more money because it's being compounded more times per year. So we had 1161.47. Now part C says how much money is in the account after those same 3 years if it's compounded continuously. So when you see continuously, you're going to think p e to the rt, what we just showed. So all I need is the p value, the principal, which is 1,000. My base is going to be e. My r is the 0.05 and t is 3 years. So I'm going to put that into my calculator. I'm putting in 1,000. Let's pop up the calculator to show everything. 1,000 second ln, which gives me e, and I'm going to do raised to the, let's do parentheses, 0.05 times the 3 years, and that's going to give me 1161.83. Now notice, since it was being compounded continuously, you ended up making even a few more cents than you did when it was compounded monthly. So we went from quarterly to monthly, and then we cut right to the chase and said compounding continuously for 3 years will have that much money sitting in your account. So the key word there was continuously. Let's go look at one last example. It says a 50-gallon barrel is filled completely with pure water and salt water with a concentration of 0.3 pounds per gallon is pumped into the barrel, and the resulting mixture overflows at the same rate. The amount of salt in the barrel at time t is given by blah blah. So they're giving us the function, which is good news. So t is time, and I guess q, or q of t, is the amount of salt. And t is time in minutes, and salt is measured in pounds. Part A says, how much salt is in the barrel after 5 minutes? Well, that's easy. That's a plug and chug. So Q is going to be 15, 1 minus e to the negative 0.004, and we're going to put 5 minutes in and punch that into our calculator, and let's see what we get. So we've got 15 times 1 minus second e ln, which gives me e, negative 0.04 times the 5 minutes, and we're going to close parentheses. So I'm doing it all in one shot. If you don't have a TI calculator, you're going to have to do step by step the e to the negative exponent, and then 1 minus it, and then multiply the result by 15. So when I push enter, I have about, I guess, 2.72, let's say. 2.72 pounds is what I have after 5 minutes. How much salt is in the barrel after 10 minutes? So same idea, except now we're plugging in 10 minutes, negative 0.004, 10 minutes. And that's going to give me, so I'm just going to go and replace, I'm going to do second, enter, and that's going to give me what I input previously, and I'm going to go in and change my minutes from 5 to 10 minutes. And I'm going to push enter, and it looks like we have like 4.95 pounds, I guess. So 4.95 pounds. So the more time that goes by, the more pounds of salt you have in your barrel, because you're pumping in pure water in the barrel with some liquid that has a concentration of salt. Part C says, draw a graph. So we're going to go, I guess, look at our TI and input that exponential function to see what the graph looks like. So let's pull up our TI. So I have 15 parentheses 1 minus second ln, which gives me e to the negative 0.04x. Let me go close the parentheses. So let's push, if we do a zoom 6, we'll have things missing from the graph. Let me go look at a better window. Let's go to like 0, since we only worry about the first quadrant. Let's go down the road to like 500, and we'll go to 0 to like 20 and look at the graph so we can get a good idea of what happens when x gets large. And it looks like it may have an asymptote going on, which makes sense because I'm looking at an exponential function, right? So I'm looking at an exponential function, e, that was reflected about the x-axis and about the y-axis and also stretched by a factor of 15, and if I distribute that 15 in, that's also going to cause me a shift up 15. So it looks like all those transformations were applied, and this is the graph I get. Now what is going to be the asymptote going through that? If I push trace, it looks like that number is close to 14.9962 in the y values. If I go to the left, it gets smaller, but it looks like it's close to 15, right? When I go all the way to the right, the y values are approaching 15. That 15 that seems like it should be the asymptote. So let's go look at it over here. So I basically have an exponential function, and there's an asymptote at y equals 15. And it's part D says, so that was part C. Part D says, use the graph in part C to determine the value that the amount of salt in the barrel approaches as t becomes large. So as t becomes large, like goes to infinity, I'm walking to the right because this is my t-axis and that's my q-axis. And as t goes to the right, notice the q value ends up being 15. So as t becomes, we'll say, large, q approaches 15 pounds. And this makes sense if you think about it, because the concentration was 0.3 pounds per gallon that was coming in to your barrel. Your barrel was 50 gallons, so eventually all of the 50 gallons of water is going to be replaced by that salt water, and that's going to give you 15 pounds that you're going to eventually end up with, because all the pure water is going to overflow and the concentrated salt water is going to take over, and the entire 50-gallon barrel will have 15 pounds of salt in it. And that was it for the natural exponential function.